All right, let's get into it. We're surrounded by software, right? It's in our phones, our cars, even our hospitals. But have you ever stopped to think about how all that complex stuff gets built without completely falling apart? Well, today, we're pulling back the curtain on the hidden discipline that brings order to all that digital chaos, software engineering.
But you know what, to really get why we need this discipline, we've got to look at what happens when it's missing. The history of software is, believe it or not, littered with some truly spectacular failures that had very, very real-world consequences.
I mean, just look at the Mariner 1 probe. We're talking a multi-million-dollar mission, years and years of work, all of it just gone in an instant. And the cause? A single, tiny, missing hyphen in one line of code. It's an absolutely mind-blowing reminder that in software, the smallest, tiniest mistake can lead to total disaster.
And the thing is, Mariner 1 wasn't just a one-off fluke. For decades, from the 60s all the way to the 90s, the whole industry was struggling with what everyone started calling the software crisis. Projects were always late, always over budget, and sometimes they failed in the worst ways imaginable. Just look at the variety here. Poor testing on a medical device that led to patient deaths, reusing old code that wasn't right for a new rocket. It became painfully clear that just, writing code wasn't going to cut it anymore.
So this crisis, it forced a huge change. It was just so obvious that we needed a more disciplined, a more structured, and just a more reliable way to create software. We had to find a better way to build.
And that approach is software engineering. Now here's the crucial point. It's not just about coding. It's about applying real engineering principles, the same kind of rigorous thinking that goes into building a bridge or a skyscraper, and bringing that to the digital world. The whole goal is to create systems that actually work, that are efficient, and that you can easily maintain for years to come.
This really helps highlight the difference. See, programming is the act of writing code. It can be a solo thing, maybe a little informal, but software engineering, that is the whole shebang. It's a huge team-based discipline that follows a super structured process to build a complete system, from the very first idea all the way through to long-term support.
And this quote just nails it, doesn't it? I mean, seriously, would you ever hire a construction crew, give them a giant pile of wood, and just say, go build me a house? No way! You'd start with a detailed blueprint. And software is exactly the same. It needs a plan, a structure, if it's going to have any chance of success.
So what does that blueprint actually look like for software? Well, in software engineering, that master plan is called the Software Development Lifecycle, or SDLC for short. Let's walk through the main phases of how something actually gets created.
The SDLC is pretty much the standard roadmap that engineers follow, and it's a really logical flow if you think about it. You start by figuring out what to build, that's requirements. Then you create the blueprint in design, and you actually write the code during implementation. After that, it's all about making sure it works through testing, getting it out to users in deployment, and then keeping it running smoothly during maintenance.
But wait, before a single line of code is even considered, great engineering starts with an even more basic question. One that's so important. Should we even be building this at all? This first step, called a feasibility study, looks at a project from every single angle to make sure it's a good idea from the get-go.
And there are a few key angles. First up, is it technically feasible? Like, do we actually have the tech and the people with the right skills to pull this off? Then, is it economically feasible? At the end of the day, will this thing make more money than it costs to build? How about legally? Is it legally feasible? Does it follow all the rules and regulations, like data privacy laws?
And is it operationally feasible? I mean, will people in the company actually use it once it's built?
And finally, is the schedule feasible? Is the timeline we've set even remotely realistic? It's only when you get a big yes to all of these questions that the project actually moves forward.
So once a project gets the green light, we hit Phase 1 requirements. This is the what phase. Here we define exactly what the system has to do. We break them down into functional requirements, things like the user has to be able to log in, and non-functional ones, like the login page has to load in under 3 seconds. This document basically becomes the contract for the whole project.
Those requirements then lead right into the next two phases. In design, you turn those requirements into a technical blueprint. This defines everything, what the screens look like, how the database is set up, all of it. Then in implementation, the developers take that blueprint and finally start writing the code, building the whole system piece by piece.
And the job is nowhere near done. The final phases are all about quality and making sure the thing lasts. Phase 4, testing, is the big bug hunt. Once it passes, deployment gets the software out into the wild for people to use. And finally, maintenance. Well, that's the longest phase of all. It's the never-ending job of fixing things, adding new features, and just keeping the system running over time.
Now, having a great process is absolutely essential, but it isn't the whole story. Great software engineering is also about the human element. It's about building with a sense of responsibility.
And this is where ethics come in. In software engineering, ethics are the moral values that should guide every single decision. It's about taking responsibility for your work, being honest about how a system works, protecting people's privacy, and making sure it's fair. It's about asking, should we do this? Not just, can we do this?
And, this isn't just some abstract idea. Major professional organizations like the IEEE and the ACM have actually created formal codes of ethics. These codes give engineers clear guidelines to help them work through tricky situations and make responsible choices.
So, let's make this real. Put yourself in this situation for a second. Your manager is breathing down your neck to release a new product. You've got a tight deadline, but it still has some major bugs that could really mess things up for users. What do? This is exactly the kind of tough spot where professional ethics really get put to the test.
So, from the total chaos of the early days to the structured, disciplined process we count on today, software engineering is really the invisible framework that holds up our digital lives. It's the blueprint that makes sure things work, and it's the ethical compass that guides the people who build them. The next time you open an app, just think about that for a second. What unseen processes, what responsible decisions were made behind the scenes just to keep you safe?
Welcome to the Deep Dive. We're here to cut through the noise and get to the heart of complex topics. Today, we're looking at something that runs almost everything digital in your life, often totally behind the scenes. Think about your banking app, right? Or hospital systems, flight control software. Incredibly complex stuff. How do we actually know these systems work? How can we trust them with our money, our health, even our lives?
That's a huge question, isn't it? And it really highlights this invisible architecture holding up our modern world. Because when that software fails, the results can be truly devastating.
Exactly. And that's where software engineering comes in. It's this rigorous discipline focused on making sure these complex systems are reliable, efficient, and maintainable. It's the hidden structure, the unsung hero, making our digital lives possible. So our mission today is to really unpack what software engineering is, how it's fundamentally different from just, programming. We'll introduce the essential roadmap for building solid software, the software development lifecycle, or SDLC. And crucially, we'll also dig into the ethics, because with this much power comes, a lot of responsibility. We think this deep dive will definitely change how you look at the apps and systems you use every day. Here, initially, you might think, building software, that's just coding, right? You sit down, type away, and boom, an app appears. But software engineering, it's much more involved than that, isn't it?
Oh, absolutely. It's a common misconception. Programming is really about the act of writing code to perform specific tasks or create specific features. It can be quite focused, maybe even informal sometimes. Great for quick scripts or, say, building a prototype. But software engineering, that's a whole different level. It's about applying established engineering principles, systematic, disciplined approaches to the entire process. We're talking about designing, developing, testing, and maintaining complete systems that are reliable, scalable, secure, and importantly, maintainable over time. It's not just about making it work now.
Okay. So if programming is like making a really good solid brick, then software engineering is like designing and building the entire earthquake-proof skyscraper using those bricks and a whole lot more planning.
That's a perfect analogy. Exactly. And for you, the person using this software, this distinction isn't just theoretical. It's the real difference between, say, a simple calculator app that might crash if you push it too hard.
Right. Annoying, but maybe not critical.
Exactly. Versus the incredibly robust, secure system that handles your entire bank account or manages patient records in a hospital. In those situations, the difference between just programming and proper engineering, it can literally be the difference between a small hassle and a major disaster.
And speaking of disasters, we really can't grasp the full weight of software engineering without looking back at what's known as the software crisis. And this was a period roughly the 60s through maybe the 90s, right? Where software projects were just notorious for going way over budget, missing deadlines constantly.
Oh, yeah?
And often ending in complete, sometimes catastrophic failure. We're not talking minor glitches here.
No, not at all. These were systemic failures. They starkly demonstrated why we desperately needed rigorous engineering practices in software. And some of these failures, they had truly tragic human costs. Take the Therac 25 radiation therapy machine. It's infamous due to some really subtle software bugs, race conditions specifically, and just inadequate safety checks. Patients received massive, sometimes lethal, radiation overdoses.
Wow. That's horrifying. It just shows how fast software can flip from being helpful to incredibly harmful without that engineering discipline.
Precisely. Or look at the Ariane 5 rocket. Exploded just 40 seconds after liftoff. Why? A software error in its guidance system. They reused code from the older Ariane 4, but didn't properly account for the Ariane 5's different flight parameters, its higher velocity. It led to an integer overflow. A classic case of failing to consider the new context for reused code.
A tiny software detail causing a multi-million-dollar explosion. And then there's that almost unbelievable story of Mariner 1, the NASA probe.
Ah, yes?
It veered off course, had to be destroyed, all because of a single missing hyphen in the code. It sounds like something out of a cartoon, but it was real.
It's absolutely real. And it underscores just how fragile software can be without meticulous, obsessive attention to detail.
And these aren't just historical footnotes, are they?
Sadly, no.
Yeah.
Even in more recent times, lessons sometimes seem unlearned. In 2012, Knight Capital, a financial firm, lost something like $440 million. In 30 minutes.
Half an hour.
A faulty software update deployed to their automated stock trading system went live, went haywire. So these incidents, from lethal radiation to financial meltdowns, they really hammer home the point. Without a structured engineering approach, the digital systems we depend on could easily fall apart. These weren't just bugs. They were preventable engineering failures.
Okay, so that context is sobering. Given those hard lessons, how do we build software today? How do we try and prevent those kinds of disasters? This is where that roadmap you mentioned comes in, right? The blueprint for doing it properly.
Exactly. This brings us to the software development lifecycle, or SDLC. Think of it as the essential framework, the roadmap for building software the right way. Just like you wouldn't dream of constructing a major building like a hospital or an airport without incredibly detailed blueprints and plans.
Right, you need structure.
Precisely. The SDLC provides that structure for every single phase, from the very first idea all the way through to ongoing maintenance after launch. It's how teams aim to meet user needs effectively, manage risks, control costs, and ultimately deliver reliable software on schedule.
Okay, so before anyone even thinks about writing code, there's a really critical first step, something that can decide the fate of a project right at the outset.
Yes, absolutely crucial. It's the feasibility study. Its core job is basically to answer one big question. Should we even build this system? Is it actually viable?
So not just can we build it, but should we?
Yeah.
Given everything.
Exactly. It assesses if the project is technically possible, if it's financially sensible, and if it's operationally realistic before you sink significant time and money into it. The outcome is usually a feasibility report. Managers, stakeholders, they use this to make an informed decision. Go or no go. It helps avoid wasting resources on doomed projects.
It's like a comprehensive reality check then. What different kinds of feasibility are we looking at here? What dimensions?
Well, there are several key ones. First, technical feasibility. Can we actually build this? Do we have the right technology, the hardware, the software tools? Crucially, do we have the skills on the team? Or can we realistically get them? And a big part of this isn't just can it be built at all, but more like can our current systems, our network, our servers actually support this new thing? Or will it need a massive, expensive overhaul we haven't planned for?
That's a really practical point. It's not just about the cool tech, but the real world integration and infrastructure.
Definitely. Then there's economic feasibility. Is this project actually worth the money? Does the expected benefit outweigh the cost? And this goes beyond just tallying up development costs. It means trying to project the long-term value, anticipating hidden costs like ongoing maintenance or maybe technical debt down the line. You really need to be convinced the benefits justify the total expense over the system's life.
Right. So even if it's technically brilliant, if it's going to bankrupt the company, probably a no-go.
Probably not a great idea, no. Next up, legal feasibility. Is the project legally sound? Does it comply with all the relevant laws, industry regulations, data privacy rules, company policies? Think about GDPR or HIPAA in healthcare or specific financial regulations. Ensuring compliance isn't optional. A legal misstep can be catastrophic, far worse than many bugs.
Good point. You don't want to build something amazing only to find out you can't legally operate it.
Wouldn't be ideal.
Yeah.
And then there's operational feasibility. This is about the users. Will people actually use the system once it's built? Will it fit into their existing workflows, or will it be too disruptive? A system can be technically perfect, financially sound, legally compliant, but if the end users hate it or can't figure it out, it's still a failure. Getting user buy-in early is often key here.
That sounds huge. User adoption really can make or break even the most clever software.
It really can. And finally, schedule feasibility. Is the proposed timeline actually realistic? Do we have the resources, people, time, budget to meet the deadlines? Are there critical dependencies? Can we, for example, get the system live before the start of the new school year or before a major product launch it needs to support? An overly aggressive schedule often leads to cut corners, burnout, and ultimately lower quality or project failure.
Wow. It's incredible how many angles you have to examine just to decide if you should even start building something. If we think back to that idea of a mobile app for rural farmers, those feasibility checks immediately get complex, don't they?
Oh, absolutely.
It's not just, do farmers have smartphones? It's, like you said, technical. Is there reliable internet access in these rural areas for the app to even work consistently?
Right, a huge potential blocker.
And economically.
Yeah.
How do you make this sustainable? How does it provide real, tangible value to justify its ongoing cost, especially if it's maybe a nonprofit venture?
Exactly. Every one of those feasibility dimensions presents potential hurdles that need serious consideration right at the start. Any one of them could be a reason not to proceed, or at least to significantly rethink the approach.
Okay, so let's say we've done our homework. The feasibility study says go. We've decided we should build it. Our blueprint is starting to form. But like building a house, just having the foundation and knowing it's feasible isn't enough. You need detailed plans for every single room, every wire, every pipe. And that sounds like the next big phase, figuring out exactly what this software needs to do.
Precisely. This is where requirements gathering comes in, and honestly, this might be one of the most critical phases in the entire SDLC. This is the process where you meticulously figure out and document exactly what the user, the client, the stakeholders need the system to do, and also how it needs to perform. All of this gets captured in a document often called the Software Requirements Specification, or SRS. Think of it as the detailed contract. It's the agreement between the client and the development team about what will be delivered.
A contract. I like that. It implies clarity, agreement, something to refer back to. So who's involved in creating this contract?
It's usually a very interactive process. You'll have clients, definitely the end users who will actually operate the system, and often business analysts who act as a bridge between the technical team and the users. If we were building that school management system, for example, you'd be talking extensively with admin staff, teachers, maybe even students or parents, depending on the features. Common ways to get this information include detailed interviews, observing users performing their current tasks. Sometimes what people say they do isn't quite what they actually do.
Good point. Observation catches reality.
Exactly. And sometimes building quick prototypes, mock-ups to give stakeholders something concrete to react to. Is this sort of what you mean?
Okay, and when we talk about these requirements, these needs, are they all the same? Or are there different types we need to capture?
Oh, definitely different types. It's crucial to distinguish them. The main ones are functional requirements. These describe what the system must actually do, the core features, the actions it performs. For our student attendance system, a clear functional requirement would be, the system must allow a teacher to mark daily attendance for each student in their class. Straightforward function.
Okay, makes sense, what the system does.
But then critically, there are non-functional requirements. These describe how the system should perform its functions. They define the system's qualities. These are things like performance targets. The system must load any page within 3 seconds, or usability. The system must be accessible and usable on both standard desktop browsers and common mobile devices, or security. All user passwords must be stored encrypted. These are often overlooked early on, but they are absolutely vital for user satisfaction, reliability, and the overall success of the software.
Got it. So speed, security, usability, maybe scalability, how well it handles growth. Those are all non-functional. They're about the quality of the experience, not just the features.
Precisely. And then there's a third category, often called limitations or constraints. These are specific rules or boundaries the system has to operate within. Things like the system must be developed using Java, or it must run only on Android devices, or maybe it has to integrate with the existing university authentication system. These are often imposed externally and shape the design choices significantly.
Okay, functional, non-functional, and constraints. And you mentioned users, clients. These all fall under the umbrella term stakeholders, right? Who exactly counts as a stakeholder?
Yes, stakeholder is the broad term. Basically, it's any person or group who has an interest or stake in the software system. They might use it directly, manage it, be affected by its output, or even regulate it. So for our school system, stakeholders would include the end users, students, teachers, internal users, admin staff, IT support, perhaps regulatory bodies, like an education ministry setting data standards, and certainly the project sponsor or client, maybe the university board who commissioned it. A big part of requirements gathering is identifying all these stakeholders and understanding and often balancing their potentially different needs and priorities.
It sounds like a minefield if you don't handle it carefully. What are some common ways this requirements phase goes wrong? Where do projects often trip up here?
Oh, there are many classic pitfalls. A huge one is simply guessing what stakeholders need instead of asking, observing, and confirming thoroughly. Assumptions are dangerous here. Another is using too much technical jargon when talking to non-technical users. It creates confusion and prevents real understanding.
Right, you need to speak their language.
Absolutely. Then there's ignoring or underspecifying those critical non-functional requirements. People focus on features, but forget about speed, security, usability till it's too late. And a really big one, failing to manage changes. Requirements almost always evolve during a project. Not having a clear process to handle those changes leads to chaos, scope creep, and dissatisfaction. If this phase isn't done well, you often end up building software that technically works, but doesn't actually solve the right problem or meet the real needs.
Okay, so we have our feasibility confirmed we should build it. We have our detailed requirement specification. We know what to build and how it should perform. We've got the contract. We've moved from a vague idea to a precise blueprint. Now, how do we actually start, building the thing? What comes next in the SDLC?
Right. With that solid foundation from feasibility and requirements, we move into the more construction-oriented phases. The immediate next step is system design. This is where the architects step in, so to speak. They take those detailed requirements and translate them into a technical blueprint for the system. This involves defining the overall architecture. Maybe it's a microservices approach, maybe it's monolithic, designing the user interface, UI, based on usability requirements, figuring out the database structure, deciding on technologies, and mapping out how all the different pieces, like the front end the user sees and the back end doing the work, will connect and communicate.
So this is creating the detailed technical schematics before the builders start laying bricks.
Exactly. You need that detailed plan. Once that design is approved, we move into implementation. This is the phase most people think of as coding. Developers take the design documents and start writing the actual code, usually following specific coding standards and using the chosen tools and languages. Often, the system is built module by module. Maybe the login system first, then user profiles, then the core features. And crucially, good practice involves unit testing. Here, developers test each small piece of code they write to make sure it works correctly on its own, catching bugs really early.
So building and testing small parts as you go, not just writing a huge pile of code and hoping for the best at the end.
Definitely not the latter. That leads directly into the dedicated testing phase. This isn't just a quick check. It's a comprehensive, multi-layered effort. You have unit tests done by developers, then integration testing, where you check if different modules work together correctly, then system testing, where the whole application is tested against the original requirements, both functional and non-functional, and often performance testing, security testing. And finally, there's usually user acceptance testing, UAT, where the actual clients or end users test the system to formally confirm it meets their needs before it goes live. This whole phase is about finding and fixing bugs and ensuring quality.
That sounds incredibly thorough. It's really about verifying everything against that initial contract, the SRS.
Precisely. And assuming it passes all those checks.
Then it's launch time.
Pretty much. That's the deployment phase. The finished, tested software is installed and configured in its actual production environment, ready for users. This might involve a phased rollout, starting with a pilot group. It definitely involves things like user training, creating manuals or documentation, and setting up the support systems needed. For our school system, this is when it gets installed on the school servers, staff get trained, and it's ready for the first day of term.
But software isn't like building a bridge, is it? Once a bridge is built, maybe you inspect it, but you don't fundamentally change it much. Software seems different. It's not really done after deployment, is it?
You've hit on a critical point. Absolutely not. The final phase, which often lasts the longest, is maintenance. This starts the moment the software goes live and continues for its entire lifespan. It covers a whole range of activities: fixing bugs that are discovered after launch because some always slip through, making enhancements or adding new features based on user feedback or changing needs, improving performance over time, and critically, applying security patches and updates to keep the system safe from new threats. It's about keeping the software alive, healthy, relevant, and secure. Like maintaining that house we built, repairs, upgrades, adapting to new needs. That makes sense. It's an ongoing commitment. Okay, if we pull back again and look at the big picture, we've talked about the complexity, the potential for disaster, the structured process. But given how much power software has, how deeply it affects everything from our finances to our health, communication, critical infrastructure, there has to be a strong ethical dimension here, doesn't there? It can't just be about technical skill. What about the responsibility of the people building this stuff? You're absolutely right. Ethics are, or certainly should be, a fundamental pillar of software engineering. It's not just an add-on. It's core to the profession. Ethics in software engineering basically refers to the set of moral principles and values that should guide professionals when they're making decisions throughout the software lifecycle: designing, developing, testing, deploying, even how it's used. It's about recognizing the profound societal impact their work can have.
So, building with integrity, thinking about the consequences beyond just the code, what are some of those core ethical values engineers should be guided by?
Well, key values often highlighted include responsibility, really taking ownership of the potential impact, good and bad, of the software you create. Transparency, being honest about how the software works, its limitations, what data it uses. Privacy is huge, actively protecting user data and respecting confidentiality. And fairness, driving to ensure systems don't discriminate or perpetuate bias, which is a growing concern with AI and machine learning systems. A simple example makes it clear. Just because you, as an engineer, can technically access certain user data within this system
doesn't mean you should.
Exactly. The ethical principle says you absolutely should not access or share it without explicit, legitimate reasons and permissions. That's an ethical line defined by principles, not just by technical barriers.
That's a very clear way to put it. It's the should versus the can. Are there official codes or guidelines for these ethical principles?
Yes, absolutely. Major international professional bodies take this very seriously. The ACM, Association for Computing Machinery, and the IEE, Institute of Electrical and Electronics Engineers, both have established widely respected codes of ethics. There's even a joint IEE-ACM Code of Ethics for Software Engineers, which is very comprehensive. It lays out 8 core principles. These cover responsibilities towards the public interest, the client and employer, the product itself, quality, reliability, maintaining professional judgment, managing ethically, upholding the profession's integrity, supporting colleagues, and promoting lifelong learning and ethical practice for oneself.
That sounds like a really robust framework, but real-world situations can get messy, can't they, where ethical principles might clash with business pressures. Let's consider a tough scenario. Imagine you're an engineer. Management comes to you and says, we have to release this product next week to meet a critical deadline, even though we know it still has some significant bugs. Maybe not life-threatening, but definitely problematic bugs. As a professional engineer bound by these ethical codes, what do you do? Where does the responsibility ultimately lie in that kind of conflict?
That's a classic and unfortunately common ethical dilemma. It puts engineers in a really tough spot. The IEECM code, for example, is very clear about prioritizing the public interest and safety. Principle 1 is act consistently with the public interest. While management pressures are real deadlines, budgets, market demands, the engineer's professional judgment, especially regarding risks to users or the public, carries significant ethical weight. It often requires courage. It means clearly communicating the risks associated with releasing buggy software. It might involve negotiation. Okay, maybe we can release with these minor issues fixed, but not these major ones. Sometimes it might even mean formally documenting your concerns, or in extreme cases, escalating the issue through proper channels, maybe even refusing to sign off on the release if you believe it poses unacceptable risks.
So it's not just a personal feeling of unease, it's potentially a violation of your professional ethical obligations to just go along with it if the risks are serious. It really underscores that the human element, judgment, integrity, communication is just as important as the technical skill.
Absolutely. Technical brilliance without ethical consideration can be dangerous. The two have to go hand in hand.
Okay, we have covered a tremendous amount of ground in this deep dive. Let's try and summarize the key takeaways. We started by seeing that software engineering isn't just programming. It's a structured, principled discipline, absolutely essential for building the complex, reliable systems we depend on, and crucial for avoiding those historical disasters like Therac 25 or Ariane 5.
Right. It's about the whole life cycle, applying engineering rigor.
Then we explored the software development lifecycle, SDLC, as that vital roadmap. It guides everything from the initial idea and that critical feasibility study, should we even build this, through meticulous requirements gathering, what exactly does it need to do and how.
That requirements phase really being the contract for the project.
Exactly. And the SDLC continues through design, implementation, coding, thorough testing, controlled deployment, and that essential ongoing maintenance.
A continuous cycle ensuring quality and longevity.
And finally, we underline that ethics aren't an afterthought. They're a fundamental, non-negotiable part of being a responsible software engineer. Guiding principles like responsibility, transparency, privacy, and fairness are crucial for acting with integrity and prioritizing the well-being of users and the public.
Understanding all these pieces really does give you a new appreciation for the digital tools we use every day.
It really does. And that brings us to a final thought for you, our listener. Considering just how deeply software is woven into every single aspect of our modern lives, from our personal chats to our national security, our health, our finances, how much responsibility do we as the users and consumers of this technology have? How much should we be demanding not just systems that work, but systems that are ethical, secure, and built with exceptional engineering quality? Maybe next time you use your favorite app or rely on a critical online service, take just a second to think about the immense engineering effort and hopefully the deep ethical consideration that went into making it safe, reliable, and truly useful for you. Thanks for joining us on The Deep Dive.